A very good afternoon, friends. Welcome all. Today we are going to discuss about model compression techniques for edge computing. Now, this will be our agenda. Firstly, we'll understand about what is model compressions, why model compression is necessary, what are the different techniques of doing model compressions. We'll understand about the different techniques and we'll implement the practical part also. And at the end, we will compare about the comparison between all the techniques. Okay, so let's start our session. Firstly, what is model compression? So model compression is a technique designed to reduce the size of the trained neural network without drastically compromising its performance. Okay, so this technique generally reduces in targeting the trained model. Okay, like for a trained model, we have to reduce some part or some portions. So what we're going to reduce? So we can reduce the model parameters. We'll reduce some model parameters that is called as pruning or low rank factorizations. Then there is decreased numerical precision. Decreased numerical precisions. Within the precisions, we are trying to reduce some precision values from here. So that is a quantization. And simplifying the model architecture. We want to, third is a simplifying the model architecture. Like while we do the knowledge distillations or architecture search, likewise. So what are the key benefits of doing this? So the key benefits is it will have smaller storage footprints. Okay, it will have faster interference and it will take lower power consumption as compared to that of like having higher or big model. Okay, like challenges in edge AI is limited computational powers, memory, and energy constraints that is there in our like local machines. So why model compression is important? So it reduces the model size and latency. It improves the energy efficiency for better powered devices. Also, it enables the real-time AI inference on edge devices. Okay, now these are some of the techniques for model compression. So we'll, one by one, we will understand about each techniques. We'll first understand about pruning. So what is pruning? So pruning is nothing but we are removing the unimportant or redundant weights from the neural network or from the trained model. Okay, we are removing the unwanted or redundant weights from the trained model. The idea is that here, many parameters contribute little to final performance. So setting to 0 and removing them can reduce the model size without significantly harming the accuracy as well. So which are having lesser weights, which are carrying lesser weights or redundant weights, okay, we can remove that parts. Okay, so there are two types of prunings. First is our unstructured pruning and second is a structured pruning. So unstructured pruning is when we are removing the individual weights based on some criteria, like like for example, smallest weight or smallest magnitude weight when we are removing. That is called as weight pruning. Then we'll have filter or channel pruning, which is also called as structured pruning, wherein we will remove the entire channel or entire filter or entire block and we will create a smaller dense model which can be accelerated easily on a standard hardware. Okay, so this is the pros of this. Like it will reduce the model size without much accuracy loss. And cons is it requires fine tuning. Post pruning will require the fine tuning of that particular model. Okay, then there is quantization. So quantization will replace high precision values, or what we can say, it will reduce the precision of weights. For example, 32-bit to 8-bit. Okay. It will reduce the memory usage and can accelerate the inference on hardwares. with native integers. Okay. So we will have here also we will have post-training quantization and quantization aware training. Okay. So post-training quantization will convert a trained model to lower precisions, which will often with smaller calibration sets, which will use to adjust the parameters. Then we'll have quantization aware training, which will simulate the quantization effects during training itself. Okay, and it will often leading to better accuracy and quantizations. So what is the pros and cons of this is it will reduce memory and it is high in computational cost. Cons is slightly accuracy drops in some cases. In some cases, we can see that slight accuracy drop will be seen. Okay, then we will have knowledge distillation. Knowledge distillation is nothing but we are training a smaller student model to replicate the behavior of a larger or a teacher model. The student will learn from a teacher's soft predictions. Okay. And whatever the soft prediction predicted by the teacher, it will be following by the student. Okay. Then the soft prediction will be trained on the smaller model. And then it will have some accuracy and evaluation scores. Okay. What is the pros and cons for this is it will maintain accuracy with fewer parameters. Okay. Means it will maintain the accuracy with fewer parameters. Okay. And computationally expensive it is. Okay. Then we will have neural architecture search. Okay. 1 minute. We'll have first low rank factorizations. Okay. Low rank factorization will use the algebra, general algebra it will use. It will use a singular value decomposition, SVD, to approximate the large weight matrices by the product of small matrices. Okay. And this is how it will going to reduce the smaller matrices. Okay. Smaller matrices will be removed. Okay. You can store like 2 or 3 matrices of the reduced dimensions from here. Okay. What is the pros here is it will reduce the computational while keeping the accuracy as is. And cons will be computationally expensive it is. Okay. Then we will have neural architecture search, NAS. Okay. Neural architecture search will automate the design of efficient architecture. Okay. So instead of manually designing or comprising an existing network, neural architecture search will explore a space of architecture or search of an architecture wherein we'll have a different types, different layer types, width, depth, to find the model that can optimize its accuracy, optimize its memory constraints. Okay. Likewise, memory constraints and other things, it will search for that part. Okay. Different layer types like width, depth, like this it will go. And search method it will follow. Okay. Then we will first see our practical implementations for these model, and then we will see the conclusion part. Okay. So here what we are doing is we are importing our libraries. Okay. Required libraries we are importing. We are importing Torch. From Torch we are importing neural networks. Okay. We are importing optimizers from here. Okay, Torch Vision we are importing. So we are importing all the necessary libraries. Here in this line of code, we are importing our publicly available dataset, which is an MNIST dataset. If you will search in a Google what is MNIST dataset, you will get to know about this dataset. This is a publicly available dataset. Okay. So we are directly calling it from a Torch Vision dot dataset. We are calling this dataset, which is MNIST dataset. Okay. After that, we are using our simple RNN. Here, we are making one just small architecture we are making, and we are using this small or simple CNN model. For this simple CNN model, we are using and training this model. Okay, here we are taking the accuracy as a matrix, and we are calling it as a baseline model. Okay, for this baseline model, as we can see, we are running only 2 epochs and it is giving us the accuracy of this much, final accuracy for this simple CNN model. Now what we want to reduce the parameters, or what we can say, we want to remove some parameters from here, or we want to compress this model. Whatever the model we have made from the scratch, instead of taking the model directly from the pre-trained, we have taken the model, we have used the model from the scratch. Now, whatever the model we have trained, which is called as baseline model, now we are trying to compress that model. For compressing that model, we are using this technique called as pruning. Right now, we have understood what is pruning. So, we are using this pruning. Here, we are using this baseline model, which we have used earlier. Okay, from where we have made the model from a scratch. We are taking that model as is, and we are using the variable name as pruned model. Okay, we are giving any variable names you can give. Okay, we are giving the relevant name for this model as a prone model. Okay, we are copying the entire model, and then some parameters we are taking from here as in weight. Okay, as in weight we are taking here, and we are using here an unstructured approach. Okay, instead of structured, we are taking a unstructured approach. And as you can see here, this is giving us the accuracy after proning. We are getting accuracy of 98.38. Okay. Now, there is one more technique, just this step, just only this step was important here. Okay. After that, what we did, we are taking only 30% from the, we are applying unstructured pruning here. We know what is structured pruning and what is unstructured pruning now. Okay. So we are using the unstructured pruning, means wherein we are only using the weights from here. Structured pruning means we will use the entire like channel or a filter. So we are not using the entire channel or a filter. We are only using some weights. The weights which are having 30% of the weights, we are taking that, or rest we are skipping. Okay, which are relevant, we are taking that. Which are not relevant, we are skipping that weights. Okay, then there is quantizations. Okay, for quantization also, we are using one baseline model, that the earlier baseline model we are taking, and we are quantizing that model to a CPU. Since we want to do the quantization, we want to compress this model, we are using this. Okay. After that, we are using this torch from quantization. We are calling, from torch, we are calling quantization dot quantize this model. Which model? This quantized underscore model. So this model we are quantizing, and we can see the accuracy of this dynamic quantized model as this much. Okay. Now after that, we'll have knowledge distillation. So as I have told you, knowledge distillation is like teacher-student. Okay. So here we will build one model which will be there for a teacher. Okay. This is a bigger CNN model, or this is a bigger model which is called as teacher model, wherein we will take all the initial layers. Okay. Convolution layer 1, 2, 3, fully connected layer 1, 2, and the activation layers, wherein we are using a ReLU activation layer, max pooling, ReLU activation, max pooling, and at the end, we are using a fully connected layer 2. Okay. So here, after that, we are getting one accuracy from this bigger model. We are getting accuracy of 99% from this bigger model. Now, what we are trying to do, we are doing the distillation for this teacher model to adapt that to the student. Student model should take that soft prediction. What is the prediction made by the teacher model, that will be taken by the student model. Okay. For that, we are using this. Okay. And here we are running only 2 epochs. If we will run more epochs, it will give you a better accuracy. Okay. We can see here the accuracy it is giving us as a 98.6%. Okay. After running only 2 epochs, we will run more epochs, it will be better. Okay. Since the model also we have taken, the model from the scratch we have taken. We have not taken the model which is pre-trained. Okay. Otherwise, it would have given us the even low accuracy. Okay. Then we are taking this low rank factorization. Within this low rank factorization also, we are using this baseline model. We are copying this model from the baseline and we are giving the variable name as this. Here we are using a SVD, singular value decomposition. We are using, you can see here, we are performing SVD here. Okay. Based on that, based on this SVD result, we will get the compressed model. Okay. After getting the compressed model, we are using here, we are using only the compressed model without any fine tuning. Okay. Without any fine tuning, we are getting this much accuracy. Okay. Since we have trained the model from the scratch, that is why we are getting this very high accuracy. Okay. Otherwise, we would have what, if we would taken the like pre-trained big model, it would have given us the like slightly low accuracy. Okay, we should have run more epochs for getting more accuracy. Like this. Okay. Likewise, we have neural architecture search. Okay. Neural architecture search also, we are using this and we are having the number of filters as 16, kernel size, kernel filter or mask, we are taking it as 3, hidden dimensions, we are taking it as 64. Okay. And this is our input layers. Within our input layers, we are taking this 28 by 28 by 1. 1 means this image is whatever the image we are taking from the MNISG, that is a black and white images. Okay. So we are using this and here you can see the kernel size we are taking as 3 or sometimes we are taking 5. We are doing this and we are getting one accuracy score as 98.38. With the kernel, this is the best accuracy, okay? From among all this, we are getting best accuracy as this. Wherever we are using a number of filter as 16, kernel size as 5, hidden dimensions, we are taking it as 64 with an accuracy of 98.38. Okay, so these are all the different models we have taken. Since the model which we have taken, this model we have built it from the scratch. You can see here, this model we have built it from the scratch instead of taking directly from the model. Okay, and the model is not very complex. Okay, that is why we are getting good accuracies. Okay, now let's jump into this again. So here you can see pruning. When it comes to size reduction, pruning is giving us the high accuracy. Okay. When it comes to speed, okay, speed of pruning is like medium. Okay. And accuracy wise, it depends upon whatever the model you are using. Within this also we have types, right? We have structured pruning, we have unstructured pruning. Okay. If you will use structured pruning, entire channel will be gone. So it will give you low accuracy in that case. Okay. Since the relevant, it might be some relevant parts also within that channel that will also remove from there. So then there is quantization, which will give you very high to medium like accuracy. Okay. Then there is knowledge distillation, which is like medium to like accuracy wise, it is very low. When it comes to like teacher-student architecture, okay, from the teacher model, whatever the soft predictions will be there, it will be taken and then it will give you the predictions for the student model. Okay. And there will be some difference between the student error and the teacher error. Okay. So that error also should be taken into account. Okay. That is there. Then there is low rank factorizations. Low rank factorizations will give you accuracy between medium to low. Okay. Then there is NAS, neural architecture search, which is like giving you the high to high accuracy. Okay. So what is the conclusion from here is pruning. When it comes to pruning, pruning will remove the unimportant parameters from here. Okay. As you can see, when it comes to pruning, it will remove unimportant weights or unimportant parameters from the trained model. Okay. Then when it comes to quantizations, quantizations will lower the numerical precisions. Okay. It will lower the precisions. Okay. Numerical precisions like 32-bit to 8-bit. Likewise, it will do. And this is how it will going to compress the model. Okay. Then there is knowledge distillation. Knowledge distillation will transfer the knowledge between what? Teacher and student model. Large model is teacher and small model will be a student model. Then there is low rank factorization, which will decompose our large weight matrices to reduce the dimensions. Okay, here what we are using, here we are using a singular value decompositions. Then we have NAS, which is a neural architecture search, which will discover, it will search from here, okay. It will search and it will discover the best or optimal architectures, okay. Near optimal, or we can say a resource constraints, which will be there, okay. So whatever we are doing here, it will be selecting the best approach, depends upon the hardware's performance requirement and the complexity of the model or whatever the workflow we are doing, okay. Or what we can do, we can do a hybrid approach also. Like we can add pruning, quantization and distillation together. Okay, once we will do this, like pruning, quantization, and distillation all together, it will give us the greatest compressions with the highest accuracy. Okay, so this will be your task for them. You have to do the hybrid approach, wherein you have to do pruning, quantization, and distillation all together within one model. For one trained model, you have to adapt all three together and check the result for the same. Okay. So this is how we have completed. Okay. Firstly, we have understood about what is model compressions. Okay. What is model compressions? It is just a technique wherein we have to reduce the size. Okay. Wherein we have to reduce the size of the model. Okay. Of the trained neural network or a trained model. Okay. So that without compromising in the performance, without compromising in accuracy. For that, we have different approaches. Like some approaches we will have like reducing model parameters. Reducing model parameter does by pruning. Pruning and low rank factorizations both does the same task. Okay. Both will reduce the model weights. They will focus on the weights and remove the weights and on unwanted weights. Okay. Whatever the weights which are relevant, they will take that. Whatever the weights which are not relevant, that will be skipped. Then there is decreasing the numerical precisions. Numerical precisions. Just how we have seen 16 byte is converted into 8 byte likewise. So it will be done by quantizations. Then there is simplifying the model architecture. If we want to simplify the original model architecture, we will use this architecture. This will be done by both knowledge distillation also and neural architecture search also. Both will go the same task. Okay, here in the knowledge distillation, we will have teacher model and the student model. And in the neural architecture search, we will going to search within the uh, uh, model that which is the best part. Only that part we are going to take. Okay. So this is it for today, guys. If you have anything you want to ask, you can share your things. Okay. Thank you for joining. This is it for today. We will meet on the next lecture with a new topic. Thank you.